Hello, my name is Christina Maria Mayr. I'm from the Munich University of Applied Sciences and I'm also part of the Vadere research group. Today I will talk about the topic towards simulating crowd guiding strategies. We all know this situation when there is a great public event in our city, for example a concert or a football game, that crowds already form on the way to the event. And my goal is to improve the safety of crowds when they are on the way to the event. And I want to achieve this by introducing a system that guides pedestrians at such places like train station or public spaces. In my research, I focus on train stations, in particular a train station in Munich. And this train station is kind of special because there are many routes to get to the train. You can see a sketch of the top-down view on the right. And what is important is that the utilization of the different routes or corridors vary strongly. More people use the shortest route, that is the route marked in red, than the, for example, longer route like the green route. So the idea is to increase the flows by distributing the pedestrians over these different routes, over these different corridors. My research question is, can we distribute agents over corridors using guiding strategies? And we will look at two simple guiding strategies, and we also will consider that not every person will respond to the route recommendation that we make with our guiding strategy. So there is a second research question: how do the different guiding strategies perform when not all pedestrians respond to it? We will test two guiding strategies for full and partial adherence. My procedure is based on simulations. The first step is to simplify the topography. As you have seen from the top-down view, the topography is quite complex. In the simplified topography, the lengths and widths of the corridors are represented, but in a simplified way. The agents, that are the virtual pedestrians, are spawned in the green source on the left. They use the shortest path to the target on the right, that is the end of every single corridor. To model the locomotion behavior, we use the optimal steps model that is implemented in the Vadere simulator. Now we come to the, for me, most interesting part, the guiding strategies. We consider two guiding strategies in this study. The first strategy is the incremental strategy. So we have 5 corridors. The shortest corridor is corridor number 1. The longest corridor is corridor 5. And every 10 seconds we recommend the next corridor. We start with corridor 1, then 2, 3, 4, 5, and then repeat the procedure. This is quite simple, and we hope that this strategy is suitable to distribute the crowd. The second guiding strategy is the minimal density strategy. This strategy is more elaborate because we measure the densities in each corridor. And then we recommend the corridor with the minimal density every 10 seconds. In our example, the 4th corridor would be recommended. So in the figure below, the density is minimal in the 4th corridor, and this is why corridor 4 would be recommended here. We also consider whether pedestrians adhere to a route recommendation or not. So they get the message, please use corridor 2, and as you can imagine, not every person will respond to that. So we consider 2 use cases. In the ideal use case, we assume that all pedestrians adhere to the route recommendation. So the adherence rate, I introduced the parameter lambda, is 1.0 in this case. But we know that this is not realistic, so we consider a second use case, the more realistic use case. And in this use case, only half of the pedestrians, means 50%, adhere to the route recommendation. And we model this with a simple discrete probability function. So let's see how the different strategies perform. Before that, we look at the normal behavior for comparison. So under normal conditions, we assume that all pedestrians take the shortest route, that is corridor 1. We observe that pedestrians move from the source to the target on the right. The agents are colored red because they have not received any route recommendation. Okay, so what does that mean for the densities? So the figure on the left depicts how the densities evolve over time. And we look at the densities between the simulation time 100 seconds and 500 seconds, that is the simulation end, because here we have a steady flow. And on the right, the corresponding density distribution is depicted. So you see that the maximum value is around 1.25. The 75th quantile is above 1, and this is only true for corridor 1 because for the other corridors the density values are 0. So there is only a density in corridor 1 above 0. Now we look how the system looks like when there is a guiding strategy involved. First, we look at the case that all pedestrians adhere to the route recommendation, means full adherence. And we start with the incremental strategy. That was the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 strategy. Okay, so the first thing we observe is that the coloring has changed. The reason is that agents have received a route recommendation right after the spawning. And in this simulation, we consider groups of 3 people. So the choice to adhere to the route recommendation is a group decision. And in the simulation, we assign this group decision to one agent. That is the agent marked in black, and the group members are marked blue. So let's see what happens. We expect that the first corridor is recommended first. That is the shortest corridor, then the second, third, and so on. Okay, so let's start the simulation. So this is exactly what we expected. Okay, so now we look at the minimal density strategy. We measure the density in each corridor and then recommend the corridor with the minimal density. Okay, so here corridor number 1 is recommended first, then second, third, fourth, fifth. Okay, then we wait a short time. Yes, and basically it looks quite similar to the results that we got with the incremental strategy. And we can also observe this in the density distributions. Okay, so first, both strategies are successful. As you can remember, the densities in corridor 1 exceeded the red threshold line. Now the densities look similar in every corridor. This is the same for the incremental strategy on the left and the minimal density strategy on the right. But keep in mind that the assumption was that every person responds to the route recommendation. And this is not very realistic. So now we need to look at the realistic use case to understand how a low adherence rate affects these densities. Again, we look at the incremental strategy first. So what do we see? We have an additional color in the setting. So the color pink marks agents that received a route recommendation but have decided against it. And you can see that pink agents are only in corridor 1 because the default behavior is to use the shortest path, and that is corridor 1. And because the incremental strategy still recommends 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, there are black and pink agents in corridor 1 at the same time. Okay, so let's see how the minimal density strategy performs, and please focus on corridor 1. So in corridor 1 there are only pink agents. Agents that have received a route recommendation and adhere to it are in corridor 2, 3, 4, 5. So corridor 1 is no longer recommended because there are already agents in the corridor. And because we measured these densities, we are able to respond to this situation. So let's see how this affects the density distributions. On the left, you can see the results of the incremental strategy. On the right, you can see the results of the minimal density strategy. And you can observe that indeed the maximum value of the incremental strategy is higher than compared to the minimal density strategy on the right hand side. This is true for corridor 1. Also, the spread in the data is larger. For both strategies, the densities in corridor 1 are higher than in the remaining corridors. However, the difference is smaller for the minimal density strategy. So this is why the minimal density strategy performs better than the incremental strategy when the adherence rate is low. Now I come to the end of my presentation. So what did we do? At the beginning we talked about the train station in Munich, where the utilization of the different corridors varied strongly. We proposed to use guiding strategies to distribute pedestrians over these corridors. And we proposed to do this using a simulation-based approach. We modeled the locomotion behavior with the optimal steps model. We proposed a simple model to model the adherence rate, means not every pedestrian will adhere to the route recommendation that we make with our guiding strategy, and we need to consider this in the simulation. We tested 2 guiding strategies, the incremental strategy and the minimal density strategy. And we found that the minimal density strategy is more suitable than the incremental strategy when the adherence rate is low. Means if only half of the pedestrians adhere to the route recommendation, this strategy performed better. And this is why we recommend the minimal density strategy and propose to test this strategy in more complex real-world scenarios. If you have any questions, feel free to contact me.